We'll let some folks get logged in, but good morning to those of you who are logged in. Anybody got any questions before we start? Cracking in just a second. I'm gonna let her.
I have a question.
Go ahead, Tia.
Do we have an exam today?
No.
Okay.
All our exams, well, I'm not say all, but from this point forward, the exams are going to be on Fridays, and the next exam is going to be next Friday. Because we got off schedule with the first one, because we actually went for 3 weeks instead of 2 weeks, covering material and stuff like that. We really could have taken it after the second week, but I didn't. I dropped the ball on that. But yeah, so the next exam is going to be next Friday.
On the 1st?
Yep.
Okay.
Then you said something about you going to a conference, right?
Yes, I'm leaving tomorrow, so I won't be here Friday.
Okay, yeah, this Friday.
Mm-hmm.
But you'll be here next Friday.
Mm-hmm.
Oh, you're good then. But no, we don't have an exam on Friday. No, we're good on that. All right. Any other questions about anything? All right, let me share my screen. Today we're gonna jump in and start talking about and start my video. We're gonna jump in and start talking about some of the kinetic and thermodynamic aspects of reactions and looking at energy diagrams and things like that. So we're going to take one of the examples on the handout and just kind of parse it all the way out piece by piece, and then use it to explain like the rest of the items that we're talking about, like the reaction energy diagram, the activation energy, the delta G, all that stuff. We're gonna take one of those examples and parse it all the way out. And then once we parse it out, we won't do it so in detail for the next several examples. But I do need to grab from Blackboard this one sheet with the bond energies on it. If you have a chance, when you go into that 2A module, there's a document. Let me find it for you. I'm gonna share my screen so you can see exactly where it is. I'll show you real quick. There's a document that you can use that has the bond energies on it. So when you calculating the enthalpy for a bond or breaking a bond or making a bond, you'll have that data. So let me show you where that is. So it's in 2A, and let's see where it is. Readings. Not readings. Supplementary resources. Yeah, let me see. Yes, so the bond energy chart is in the assignments folder, and it's in a folder entitled supplemental readings for 2A. So it's this chart right here. So I'm gonna pull this up and download it. So here on this chart, it gives you like the bond strength, and this is what you'll use to calculate delta H. Anytime you need to calculate a bond breaking or bond being formed, you'll use these numbers. The top number is in kilocalories. Notice it's smaller because it's like 4.184 kilocalories for every kilojoule. So it's 71 kilocalories for an HI bond. So this is the bond right here, HI, and you read it across. This would be CI, and then CBr, CCl, CS, CP, like that. You can use either kilocalories or kilojoules. I like to use kilojoules personally, but you can use either one as long as both bonds, the energy or the bond strength is in the same units. You're subtracting them. But we're gonna use this. So I want to download this and have it handy. And I'm gonna upload it into the chat for you.
Yeah, it's not on Blackboard yet.
Hmm?
It's not on Blackboard yet. In our view.
It,
Under
2A is open, right?
Oh yeah, it's open.
Yeah. If you go in the assignments module in 2A, it's right here in this folder. Is that folder not visible to you? Because it's saying that it's available.
Okay, you said under assignments. Okay,
Yeah.
I went to supplementary.
Yeah, no, it's under assignments. It's a folder right here in assignments. All right, let me upload that to the chat. And that way you don't have to hunt for it. You can just grab it and download it. All right, so that bond energy chart is in the chat. And yeah, that's what we're gonna use when we start calculating delta H and things like that. So let me switch back to my iPad. And we're gonna jump in and do one of these examples in great detail. And then we'll take what we get from that and just push it for the rest of it. All right. So now I'm gonna leave this because I think we did this on yesterday. I'm gonna make this for you, right? You should be able to, based on what we've done with the other examples, you should be able to tackle this problem. And if you can't, if you get stuck or something like that, just reach out. And we'll do, trying to think about Thursday. We'll do a study session on Thursday. I'll send you the time because I got a pretty packed day, but we'll do a study session. So anything you don't get or understand, especially if it's an on your own problem that I've assigned, bring it on Thursdays and we can discuss it. All right. So we talked about the elimination. We talked about substitution. I said I was going to move that off that line. Same problem from yesterday. All right, I'll figure it out. Let me just go here because we're on the second part of this handout. And what it asks is to supply the arrows, identify, and this is all, again, reps and practice. The more you see it, the better you're going to get. It asks you to identify nucleophile, electrophile, and what type of reaction, addition, substitution, elimination, rearrangement, and what is delta H, is it exothermic or endothermic, and what is KEQ? Is it greater than 1 or is it less than 1? All right. So I sent you a couple of videos that kind of discuss all of these thermodynamic and kinetic topics, but we're going to take this example right here and we're going to beat the crap out of it. And we're going to find all of these pieces of information based on what we have here. So I'm going to cut this out, put it on a new sheet. All right, I'm going to paste this here. All right. So the easiest part of this is putting the arrows in at this point, because all the other information is going to be, we have to figure that out, right? Based on, this is all new stuff at the end, but the arrows are not new. So in this particular example, where's my nucleophile? And how do you know it's a nucleophile?
Is it the innate?
Yes, this is my nucleophile. My nucleophile can be negative, or it could be neutral. But it's always going to have a pair of electrons to donate. And it's not necessarily a lone pair, because some nucleophiles can actually be a part of a polarized bond, like an organometallic, which we'll study that in part 2. But for the purpose of this class, your nucleophile is going to have some lone pairs to donate. So that's my nucleophile. That by default, this is my electrophile. And if we look right here, right, if you want to know where the electrophile is going to get attacked, look for the most polarized bond in the electrophile. And in this case, is here, because you have a huge dipole here. Right, where the carbon is partially positive and the oxygen is partially negative. Right, and if you look in the product, you can see what happened. Right, there's a new bond between the carbonyl carbon and nitrogen. So you can see what happened when the nucleophile attacked. What would that be called right there? That species or structure in the product. What's that an example of? Right,
Isn't
we
it?
added something to a carbonyl, a nucleophile to a carbonyl. What would that be an example of in the product?
Is it elimination?
No. I mean the actual species itself. Is that not a tetrahedral intermediate? All right, it's not going to stay that way, and eventually it will eliminate Sanaya, but that'll be another step. So let's put the arrows in. Where are the arrows going to start and where are they going to stop? Again, if you're reacting a nucleophile and an electrophile, your arrows always start at the nucleophile or the source, and they end up at the electrophile, which is the sink. Right, so source to sink. So where do I start my arrow?
Would you start it coming from the electrons from the N?
Yes, this is my source. So I'm going to start here, and I'm going to use that pair of electrons to attack that carbon. What else has to happen when I attack a pi bond? I'm adding to the pi bond, right? Does it stay intact or do I have to break it?
Break it.
I have to
Yeah.
break it. Right, so those pair of electrons are going to go up to oxygen. So that's how I got to here. Are y'all following that?
Yes.
All right. So now we're good with the arrows. We identified the nucleophile and the electrophile. What type of reaction is that? Remember, if either of my star materials is a pi bond or contains a pi bond, and that's the reactive site, it's not going to be a substitution and it's not going to be a rearrangement.
Elimination.
Okay, so look at the product. What's always the outcome of an elimination? You make a pi bond, right?
Oh,
So what's the reverse of making a pi bond? Breaking one, is that right?
Addition.
Mhm.
So this is, yeah, so this would be considered an addition reaction. All right, are we okay with that? That this is an addition. I added a nucleophile to a pi bond. So that's an addition. All right, now we need to get into the thermodynamic part, right? So we're going to calculate delta H. And the way we calculate that, and remember from, hopefully you remember this from Chem. Do y'all remember this equation from Chem?
Yes.
Yeah.
Yes.
Dealing with the Gibbs, the free energy. So the free energy is the enthalpy minus T, which is the temperature, times the entropy. Right? So if you eliminate the entropic effects, right, in essence, delta G is roughly equivalent to delta H. Right? So delta G is a thermodynamic term. And that controls like equilibrium. All right. So in order to calculate delta H, there's a simple formula that we can use to calculate delta H. That's why that bond energy sheet is so important. To calculate delta H, we can subtract bonds broken. Well, let me not say that because I don't want to get us in trouble early. The sum of bonds broken minus the sum of bonds formed, right? And when we talk about the bonds broken, we're talking about the energy of that bond or the bond strength. And then all right, everybody okay so far?
Yes.
All right, so let's go back up here. What bonds did we break in order for this reaction to happen? What did we break?
The carbon to oxygen pi bond.
Yes, we broke a carbon oxygen pi bond. And then what do we make?
Say carbon to nitrogen bond.
Excellent. CN sigma bond. We broke a CO pi bond and we made a CN sigma bond. All right. So now let's look at the chart. And I did upload it to the chat. So go ahead and grab it. Let's look at the chart for a carbon oxygen pi bond. If you look at that chart, you can see at the bottom, it has some multiple bond energies. You see C double bond O down there. 177 kilocalories or 741 kilojoules per mole.
Doesn't matter which one we use.
Let's use kilojoules. But if we use kilocalories, everything has to be in kilocalories. If we use kilojoules, everything has to be in kilojoules. So 741 kilojoules per mole for breaking or making a CO pi bond. That's the energy you're either gonna release or you're gonna absorb. All right, and then for the CN sigma, You go up on the chart, find carbon in the chart, which is on the second row, and then go across until you get to nitrogen. And the number should be 305. Do y'all see that?
Yes.
So it's 305 kilojoules per mole. Anybody not following that?
I don't see it.
Do you have the chart in front of you?
Mm-hmm.
You see carbon on the second row under hydrogen?
Mhm.
Go across that, all the way across until you get to the nitrogen that's in the top. You see the nitrogen up top?
Mhm.
All right, do you see the number
Okay.
73?
See what?
The number 73 on the line, on the same line with carbon?
Mm-hmm.
And then underneath that's 305?
Okay.
Yeah, that's the bond strength for a carbon nitrogen bond. All right. So now we have our numbers, we can put those into this equation. So, and the reason I say sum is because sometimes you're gonna have multiple bonds broken and multiple bonds formed. So you take the sum of the bonds broken and the sum of the bonds formed. Right? If you have more than one bond that's broken, then you got to add those values up to get the total. We got more than one bond that's formed, add those values up. So 305 is bonds formed. So now we just need to subtract this out. So delta H is going to be 741 kilojoules, and keep the units per mole, minus 305 kilojoules per mole. Right, what is that? 436? Is that right?
Yes.
Right, notice it's positive 436. That's a huge number, right? That means that it takes a lot of energy for this reaction to take place. And with delta H being such a big number, right? That means that, and it being positive, that means that the reaction is endothermic. Sometimes you'll see in a book, it says, it might say endergonic, same thing. It means it needs energy in order to go. It's not spontaneous. Are y'all following? Yes, no?
Yes.
Yeah.
All right, if delta H is positive, that means that the free energy, delta G, is also positive. So for endothermic reaction, delta G is positive and delta H is positive. And so what we can glean from that is we can think about now what the reaction energy diagram would look like for this reaction, right? If it's, and we're not going to do this, this is an approximation, it's not going to be precise, right? But if we take the energy diagram, you should have seen this if you watched that one of the last or the first video, second video I sent the other day. You should have seen what this looks like. So on the x-axis, it's time. Right, and all this is a depiction of the energetics of a reaction. You know, if it's exothermic, if it's endothermic, the curve is going to look different for each type of reaction. So on the X is time, on the Y, so I can fit this in here, it's energy. All right. If it is exothermic, what that means is that the product energy is higher than the reactant energy. That's what that means. So the gap here between product and reactant, that is your delta G value. Right, your Gibbs free energy. So, and you calculate that by the products minus the reactants. So if the energy of the reactants is lower than the energy of the products, then delta G is going to be positive. If the energy of the products is lower than the energy of the reactants, then delta G is going to be negative. Right? So this is what the curve looks like for a exothermic reaction. And then at the top part of this curve, what is that species called? That's at the very top, the highest energy species that's on the reaction curve. Anybody?
Can you give us a hint?
I'll just write it out. It's called a transition state. All right, that's your highest energy point. And in the transition state is exactly what it says. It's transition is happening. So the reactants are being converted into the products, and bonds are being broken and bonds are being formed. So you got partially broken and partially formed bonds in the transition state. Right, so let me give you an example of what that would look like. Let me add a page here for this particular reaction. And then we'll come back to all the numbers and stuff. So in this case, we have a carbonyl, which looks like this. It's trigonal. And so when that nucleophile attacks the carbonyl carbon, it's gonna, let me just say, let's just say for the sake of this example. Was it just NH2? Or was it NHCH3, sorry. Let's say for the sake of this example, it's going to attack from this top face, like so, right? So we already put the arrows in. So what we'll have here is a partially formed bond between nitrogen and carbon. This is partially forming. Right, and then for that pi bond that we're going to break and give those electrons to oxygen, that bond is partially broken. So we'll draw it like that. You always, to show a partially formed or a partially broken bond, you just use a dashed line, right? So this is partially formed, and then this is partially broken. So this is what the transition state for that reaction would look like. And you illustrate or you denote that it's a transition state with a double dagger, so that whenever you see that symbol, looks like a, well, y'all never seen a, some of you may have, looks like an old school telephone line or utility line. Whenever you see that symbol, that's indicative of a transition state. And it's exactly, the terminology is exactly what it says. There's the transition is happening from reactant to product. So as the reactants and interact and they become the product, there's a place on the energy curve, the highest energy peak on that curve or point on the curve that we call the transition state. That's for any reaction. And it involves partially broken and partially formed bonds. Go ahead. I see 2 hands up.
So I had a question earlier on the graph. You said
Mhm.
it's exothermic, but I thought it was endothermic.
Did I say exothermic?
Yeah.
Yeah, my bad. But I wrote down endothermic.
Okay.
I just misspoke. Yeah. All right. Go ahead, Tia.
Yeah, so for the transition state,
Mhm.
why are the bonds partially broken if that's the highest energy point?
Well, it's not going to be fully broken until I get to the product, right? So all the way up that energy curve, the extent of bond breaking is changing, right? At the very beginning, there's no bond breaking, there's no bond making. But as you move up the curve, right here, you ever seen that little game on Price is Right with the little Swedish man? I forgot the name of it. I don't know if it's
Climb the hill.
yeah,
Something like
yeah. As you going here up the hill, right? The extent of bond breaking is changing, right? But it's still partially broken, even here. Uh-oh, that didn't work out. It's still, even there, it's partially broken. Now, it could be more, the bond that's formed could be more fully formed.
Mhm.
You understand what I'm saying? But it's not going to be full until you get to the products. But that brings up another
So,
point. Go ahead.
so at that on the graph, at the
Mhm.
point where like I guess the amount of energy kind of drops,
Yes,
is that the point where the bonds are like fully formed?
yes. And even then, the extent is not complete until you get to the point right here where you have the product.
Oh,
Mhm. That's a great
so
question.
it's still partially broken
No, now
until
when
it
you
gets
get
to that
to,
point.
yeah, when you get to the on the other side of the transition state, right? Your bonds that are
Mhm.
formed are basically, let's say 99%, and your bonds that are broken are 99%, right? Especially in an endothermic reaction. Because if it's endothermic, the time that you're taking to go from reactant to transition state, your transition state is going to almost look just like your product based on the Hammond postulate. I think I sent that video too. So since you asked that question, so the transition state for endothermic reaction is going to almost look identical to your product. It's because it's a late transition state. And that's based on what we call a Hammond posture, right? Which says that the transition state, if it's late, it's going to look more like the product. If it's early, it's going to look more like the start material, right? So there'll be extensive bond breaking and bond making for the transition state for endothermic reaction. So if it's endothermic, we say that it's a late transition state. Because look at all the time you've taken. Let's just look back at the diagram. Look at all the time you've taken getting to the transition state. and how much time is taken getting to the product. It's a lot more time was expended getting to the transition state than to the product. So by the time you get there, it's going to almost look just like the product.
Okay, so, and you said if it's exothermic, then the transition state would be considered
Early.
early?
Yeah, it's the opposite. We're gonna do it. Yeah, we're gonna pick another example that's an exothermic reaction, and then all this stuff is gonna be reversed. So the curve is gonna look totally different. The extent of bond breaking and bond making is gonna be totally different. The delta H is gonna be negative instead of positive. So for something that's exothermic, it's the exact opposite for everything.
Mhm.
How does the endothermic reaction look identical to the products?
Not the reaction, the transition state. And it's because of where it is on the curve relative to the product. You see how close in energy it is to the product?
Yes.
Yeah, so if you look right here, this is the difference in energy between the transition state and the product, right? Very close in energy compared to the transition state and the reactant, right?
Oh.
Big difference. And so what the Hammond postulate states, said a different way, that for endothermic reaction, the transition state will look almost identical to the product. The reason is because it's a late transition state. And the second reason, the second part of that is that it's closer in energy to the product.
I have a question.
Go ahead.
Okay, can you go back to the graph?
Mhm.
So if the reaction is exothermic,
Mhm.
would the reactants be identical to the transition state?
Yes, they will be very similar. There'll be very little bond making and bond breaking because it's a spontaneous reaction. So it happens so fast that the transition state and the reactants are almost identical. Right, the extent of bond breaking and bond making is not very far along. So the transition state is going to resemble the starting materials for exothermic reaction. All right, these are great questions, by the way, because it forced us into talking about the Hammond postulate, which is a very important topic anyway. All right, so we know that this is endothermic. We know how to calculate delta H. We know that delta H and delta G are roughly equivalent. And if it's positive, then we can also make an approximation for that equilibrium constant, KEQ, right? If it's endothermic, KEQ is going to be less than 1. If it's exothermic, KEQ is going to be greater than 1. All right, so for endothermic reaction, in this particular case, KEQ, which is the equilibrium constant, equals, or not equal, is less than 1. Right? Does anybody remember what the equilibrium constant measures? Anybody?
Is it the rate of at which the products and the reactants are equal?
Yes. So it's not necessarily the rate, but it's basically measuring the extent of equilibrium and going from reactants to products. So this is the basic equation for what you're looking at. The concentration of the products over the concentration of the reactants. So you can imagine for endothermic reaction, right? The products are very high in energy and the reactants are low in energy. And so when you measure that ratio of products to reactants, there's very little product compared to reactants. So that's why that number is going to be less than 1, because the R on the bottom is going to be a bigger number. All right. Is this making sense? Is anybody not catching it, or is it making some kind of sense? If you, I think I sent the videos out Saturday, so some of it you may not have watched yet, but if you watch the videos after this class, it'll probably all gel and coalesce. Yeah, so we've calculated delta H. We know what KEQ is. We know it's endothermic, how to tell if it's endothermic or exothermic. And so now let's look at we got time. Yeah, we got time. We got 6 minutes. Let's look at another reaction. Let's look at the second part of this reaction. So we're gonna take this one. And I'm gonna paste it on a new page, and we're gonna work through it just like we did that. All right, so let's put the arrows in first. In this particular case, there's no nucleophile or electrophile, so I'm not gonna worry about that. But let's put the arrows in and see what type of reaction this is. So what do you think? We started out with this tetrahedral intermediate, and we ended up with a carbon-oxygen pi bond and the loss of a group. What type of reaction is that? It's an elimination, isn't it?
And that's which one? That's which one again? We're losing what again?
You lost, if you look from left to right, you see how you lost the OCH3 group,
Okay, yeah, I see what you're
and
saying.
then you formed a carbon-oxygen pi bond. All right, so if we put the arrows in, we'll see that it's here. And here. Right, those are the two arrows that show that elimination mechanism.
Is it because a pi bond is being formed in the?
Yes.
Okay.
Yeah. Elimination is always going to give you a pi bond in the product. That's how you can, that's what makes it so easy to spot. Anytime you form a pi bond, an elimination happens. All right. So now let's go ahead and go through the rest of this, all of this good stuff. Well, let's calculate delta H. We're not gonna go through every single thing, but we'll calculate delta H. And we'll draw the energy diagram for it. So bonds broken will be what? Did we break a CO
Maybe.
sigma bond? Right there.
360.
You said 360? Yeah, I
Mhm.
think that's right. And then we made a CO pi bond, didn't we? Is that right?
Yes.
And that was what, 741?
Yes.
So that's going to be what, negative 381? Is that right?
Yes.
Negative 380. So that's it. Again, this part is highly exothermic, right? Highly exothermic, because delta H is negative. So if delta H is negative, that means that delta G, the Gibbs free energy, is also going to be negative. Is that right?
Yes.
And it means the reaction in this case is going to be exothermic, right? So the energy diagram for a reaction that's exothermic, and then again, this is an approximation, it's going to look like this, where now your reactants are higher in energy than your products. So this is reactants. This is my product. Right here is my transition state. right? And then this is the difference in energy. That gives free energy, right? And then this is my, I don't think I put this in the other example, but we need to talk about it. This is my activation energy. Right, that's the energy that it takes to get over the hump, right? To get to the transition state. Notice,
I have a question.
go ahead.
Can you repeat what that symbol is above the
The double dagger.
Mm-hmm.
Yeah, this is the, that's my transition state.
Oh,
Sometimes you'll see it really fancy looking, but. All right, so that's your activation energy, your Gibbs free. In this case, is products. Delta G naught is, come on, Russell, get it together. Products minus reactants. Notice the products here are lower in energy than the reactants. So this number is going to be negative. All right. What about if it's exothermic or exergonic, which you might see in your book? We know about delta H, we know about delta G. Look at the activation energy, right? It's very low. So for exothermic reaction, it's going to have a low activation energy. All right, what the other thing that we know is what we just talked about for the endothermic reaction. Look at the difference in energy between the reactants and the transition state. I'm going to change colors with this. Can you see that? Versus the product in the transition state. Big difference, right? So in this case, the reactants are closer in energy to right? Closer in energy to your transition state. What that means in terms of the extent of bond formation is there's minimal bond breaking and making, and the transition state is going to resemble reactants, right? See how that's the reverse of the endothermic, because you had so much time between the reactants and so much of a huge energy difference between the reactants and the transition state that by the time you get to the transition state, you almost look just like the product. Here, because it's such a short distance between the reactants and the transition state, and there's such a small energy difference, then the reactants they don't have as extensive of bond making and bond breaking as you would for an endothermic reaction. So your transition state is going to look very similar to the reactants, not very much bond making and bond breaking. It's really fast and spontaneous. Right, so your activation energy here for exothermic is low. The delta H is negative. Delta G naught, which is the Gibbs free energy, is negative. And your transition state and reactants they look similar to one another. Right, and I know this is a lot, and I did that on purpose for these first two examples, because it's good to get all this stuff out in the open. Also, AEQ is gonna be greater than 1. Uh-oh, sorry. But I'd rather spend more time on the front end. And then when we get to the other examples, we could just zip through them. All right. So we're gonna pick up on Friday with this sheet, continue with this sheet until we're done with it. And then we'll start a new topic after this. Because we still got to cover radicals, but that's not gonna take, that's a day, 1 day dealing with radicals. All right, any questions? Anybody got any questions before we log out? Make sure you watch those videos that I sent this weekend. Because if you didn't, and you came in cold, this is all brand new. But if you did, then it's just a refresher. But if you haven't, and you watch it after today, it might help the information to kind of coalesce and come together. So make sure you watch it if you haven't.
Were the other videos that you sent out? I think it was like yesterday or the day before. Is that for next week?
What was it? Which video? Was it wasn't it all dealing with this? Kinetics, and then Hammond Postulate, and there was something else in there. I can't remember all the links, but there were multiple links in that last announcement. I'll have to go back and look.